So this video I'm going to teach you the basics of exponential modeling. We'll start with, there's basically two equations that you can use for exponential modeling that I'm going to talk to you about. Two basic forms of exponential equation. There's the the second one is exponential growth based e, and the first one is exponential growth in any other base. So in both these equations, a is the initial value, it's both a's here, and this one, b, is the growth or decay factor, not to be confused with the growth or decay rate, and and k is the constant. Excuse me, no, we're going to say the continuous growth rate. Okay? So, main point that I want to point out to begin with is that anything that's written in this form can be changed to this form and vice versa by the simple fact that b is equal to e to the k. And you can see that e to the k to the t would be the same thing as b to the t if those are equal to each other. So for example, if I have an equation like y equals 1000 times 1.05 to the t, and let's say I wanted to write it in the second form, I know that it'd have to be y equals 1000 because the a's are the same, and all I need is to figure out what k is. So I know that 1.05 is equal to e to the k, and then I solve for k. And of course, when I have an exponential in my equation, I solve using logarithms. So I take the natural log of both sides, and when I take the natural log of this side, natural log of the e to the, cancel each other out, and I'm left with just a k. So that means that k is equal to the natural log of 1.05. And if we throw that in our calculator, 1.05 natural log, 0.0488. So that'd be 0.0488 is approximately equal to k. I rounded off, so it's approximate. So then this would be 0.0488t. So these two exponential equations are going to model the same thing. Okay? So that's the first thing that's really important to understand, is the connection between the two. The second thing is, let's visit the first equation a little bit more. So when we have y equals a times b to the t, I said earlier that b is the growth or decay factor. So it's growth factor when b is greater than 1. That's a decay factor when b is less than 1. Now, when we say decay, we don't mean like rotting things. We're saying that decay is the math word when things are getting smaller, and growth is the math word when things are getting bigger. So this, you can look at an equation like, for example, the one we had up here. We knew this is a growth equation because 1.05 is bigger than 1. Okay, so growth factor, decay factor. And notice we're calling them, again, factor, not to be confused with growth rate or decay rate. So what is the relationship between growth factor and growth rate, or decay factor and decay rate? That's a very good question. Glad you asked. So the connection is b is always equal to 1 plus the growth rate or the decay rate. for example, if something is growing 5%, that means that, let's say 5% a month, that means that every month we're going to have 5% more than we had the last month. And so if I have something and I want it to grow 5%, I have to multiply it by 1.05, because if something grows 5%, that means I have 105% of what I had before. The 1 just gives me the original amount, and then the times 0.5 gives me the growth. Okay? And you can see the same thing happens with decay. If I'm decaying 4%, let's say, then that means that I'm losing 4% of my stuff. That means that I have 96% of my stuff left over. So notice that 0.96 is equal to 1 plus negative 0.04. So if we want to represent a decay rate as negative and a growing rate as positive, then this function, this equation works no matter what the rate is. So that's the basic idea of these things. You should be able to switch back and forth between the two using this relationship right here, and you should be able to understand that A is the initial value, which means it's where I start, and recognize a growth factor from a decay factor, and finally know how to get a growth rate or decay, to get a growth factor or decay factor from a growth rate or decay rate.